So let's look at some examples of hydrogen bonding and trying to identify it. Again, the first thing you're trying to look for is first, do you have dipole-dipole interaction? And again, this could be two of the same molecules, or they could be different. So in this example, we have methanol and water. We can see the partial negative charge of methanol here and the partial negative charge of oxygen of water here. And looking for that pattern that we talked about of that X chemically bonded to H and then being attracted to the lone pair on some element Y, we can see by looking for that pattern, this is our X chemically bonded to our H, and then the oxygen here is our Y. And so this is considered hydrogen bonding because X and Y, are equal to nitrogen, oxygen, or fluorine. In this case, X and Y are both oxygen. Even though they're different elements or different compounds, it's still considered to be hydrogen bonding. We can see the same thing with methanol to methanol. So this is an example of it being the two same molecules. We again see that we have a dipole-dipole interaction, and we can see here's our X chemically bonded to our H, here's our Y with its lone pair, and there's our hydrogen bonding. This is the hydrogen bonding between ammonia and water, and we can actually flip this around too, so I'll only demonstrate that in a second. So here's X bonded to H, here's our Y, which is our nitrogen now, and we have our hydrogen bond. We could also do that on this side because we know this is the negative side of ammonia. So if we had water, for example, this side's slightly positive, and so here's our X bonded to H, our attraction portion to Y, which is our oxygen, and so that ends up being hydrogen bonding also. So when you're doing these intermolecular forces, it can be very tricky because you have to make sure you're looking at and rotating this all around, that there's lots and lots of different ways that you can look at this and lots of different ways that you can get different answers. Another example would be here on methanol also, because you could have another methanol molecule, let's say here. And we have to be very, 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 very careful, because would this attraction be hydrogen bonding? And the answer is no, this is not, because if we do X chemically bonded to H attracted to our Y, X here is carbon. And so this is not hydrogen bonding. This is only dipole-dipole interaction. So you can have multiple answers at different positions and different orientations, and different, looking at it in different ways. So you really got to go back. This is why it was so important to be able to see this in 3D and be able to rotate these structures and see exactly what they're doing. Hydrogen bonding is responsible for a lot of different things and many unique properties of water. This is why we keep on using water to demonstrate hydrogen bonding. The hydrogen bonding in water is extremely strong, and this is because of this bond angle, the lone pairs that exist, the extreme difference in the electronegativity of oxygen and hydrogen, and it's responsible for so many things. It's responsible for the structure of ice. This is the crystal structure of ice, where you have this open blank spaces in it, and it traps, creates the density of ice to be lower than that of the liquid, and that's why ice actually floats, and because of these little gaps that form in the actual solid structure of ice or of water. You can see that here. Because of that lattice structure, you can see that the density of ice is lower than that of water, and so then that's why it floats. It also has a really high specific heat capacity for such a small molecule. It doesn't have a relatively high molar mass, but its heat capacity is huge. And because of this heat capacity being so large, this is why water controls, the oceans control all of our environment and our whole atmosphere and our whole ecosystem. And so it's a very special molecule because of that ability, its structure and its ability to have so much hydrogen bonding.
Points of the group 6A. A plot of the boiling points of the group 6A hydrogen compounds shows a trend. Based on this trend, we would expect the boiling point of water to be here. In reality, H2O's boiling point is much higher. This is a consequence of water's stronger hydrogen bonds.
As we can see that we're using our boiling point to measure our overall intermolecular force. And so if we look at all of these, as we increase our mass, our boiling point goes up, which makes sense. We have more electrons. This is the influence of the last one, which is called London forces. But what we see is this increase for these three molecules. And the reason why is even though they're lighter, they have higher boiling points. And this is because all three of these have hydrogen bonding.
On average, the electron cloud of an O2 molecule is distributed symmetrically across the molecule. The molecule is not polar. A water molecule, which is polar, repels the electron cloud, causing it to be asymmetrically distributed and thereby induces a dipole in the O2. This shift allows O2 to be weakly attracted to the water molecule.
And so this is called dipole-induced dipole. Where you're taking a polar molecule and you're actually taking it and inducing a dipole moment on a nonpolar molecule. This is done because you usually have a substance that's extremely polar, and as it gets associated with something that's nonpolar, it causes a shift in its electron cloud, creating these partial charges and therefore inducing a dipole moment and allowing it to be attracted to one another. Again, this is a very weak attraction force. This is why you can't dissolve a lot of oxygen or hydrogen or nitrogen in water, because it's really, really weak. It doesn't have that ability to have a great attraction. You can see oxygen can only dissolve a maximum at 20 degrees Celsius of 0.000434 grams for every 100 grams of water. So it's a relatively small amount. What you do see is an increase here as you go down, though. And so why would that be? Why does this actually increase? Well, if you look at it, as I go down, I'm increasing the solubility. As I go down, my molar mass increases. That molar mass leads to more electrons. And because it has more electrons, this cloud has a larger polar ability. It creates a larger dipole moment when it's induced. And when that does that, it ends up being attracted more, and therefore you're able to dissolve more. So this idea of molar mass's influence, we're really going to talk about when we talk about the last one, which is coming up next, which is called London forces. This is the same thing true. This is also true when you talk about iodine dissolving in alcohol. This is commonly used as a disinfectant. Way back when, nobody uses it that much anymore, but you used to have dissolved iodine in alcohol, and you'd put this on a cut to kind of disinfect it. It obviously burned and hurt a lot, but the reason why you can dissolve this iodine, because it's normally nonpolar, is because of the strong ability of this alcohol having, or this ethanol, having that bent structure and having a large dipole moment, and therefore inducing a dipole moment on iodine.
An iodine molecule has, on average, an electron cloud that is symmetrically spread over each iodine atom. I2 is not polar. The attractions or repulsions between the atoms of I2 molecules can distort their electron clouds. Dipoles can thereby be induced momentarily in neighboring molecules.
And so this is, again, called induced dipoles, where you're taking two non-polar molecules. Oops, let me rewrite that. where you're taking two nonpolar molecules and you're actually creating them to have a intermolecular force. Now, normally when they're by themselves, they're not going to be attracted, right? Because there's no partial positive, partial negative. But because everything on the outside is electrons, if you force them to interact with each other, kind of by increasing the pressure or pushing them together, they're going to end up seeing their electron clouds, which is what you see here. And as that happens, it's going to eventually push electrons to one side. And this kind of has that cascade effect. So once it induces, all of a sudden it starts to cascade across the whole substance, and then you end up coalescing, or you end up liquefying it. This is an example of liquid nitrogen. Nitrogen is a nonpolar substance, and it's about 70, your atmosphere is about 78% nitrogen. And so normally nitrogen gas is a gas at standard conditions. But you know liquid nitrogen exists. And what's happening there is, yes, we're cooling it off, but we're also pressurizing it. And that pressure forces the nitrogen to kind of see each other. And when they see each other, they see each other's clouds. And when they see each other's clouds, that dipole moment can be induced. The thing about London forces.
In the flask is solid iodine. In the test tube is ice. When we heat the iodine, its weak induced dipole forces are overcome, and the iodine sublimes into the gas phase. The gas recondenses as a crystalline solid on the cold test.
The thing about these things is that they always exist because it's based upon position. They're relatively weak, they're not very strong, but they can also help almost magnify the other substances' ability that are already polar. So because London forces always exist no matter what, really what we need to take care of is the fact that it has to do with the number of electrons, how much it likes to distort. And so we can see this example with just higher molecular weight, that if we have a higher molecular weight, this is giving us more electrons. The more electrons I can push to one side. If I push those electrons to more than one side, this creates or magnifies almost that dipole. And that's true whether or not it's already polar or if it's not polar. So even if it's not polar, if I have more electrons, I can induce a stronger dipole moment because I have more electrons to push to one side. If it was polar to begin with, if I have more electrons, I can magnify that polarity because I have more electrons to push to one side. And you see that. If you look at the molar mass, if you just look at methane, ethane, propane, butane, you can see as we increase the number of carbons, our boiling point goes up. And you can see that graphically here, which makes sense because we're plotting our molar mass versus our boiling point. And so whenever you're thinking about this, London forces, since they always exist, we got to make sure that we have that ability to recognize that. So looking at this chart, it's important. So really what we're doing is we're trying to look at the overall strength of the overall intermolecular force. We're doing that by the boiling point, meaning if we have a high boiling point, we're going to have a relatively high or strong overall intermolecular force. This boiling point is influenced by three different things. Number one, the type of intermolecular force, one of these. If I have a high intermolecular force, a strong intermolecular force, whoops, didn't want to do that. If I have a strong intermolecular force, I'm going to have a high boiling point and therefore a relatively high overall intermolecular force. If I have a high molecular weight, I'm going to have a high boiling point and therefore a large overall intermolecular force. When you do the lab, you're going to investigate how structure has to deal with that. And that's that worksheet that we're working on, or you're working on in the lab.